Hello, this is Ariail. This is my Physics 2211 Lab 2 presentation. The purpose of this lab was to observe the motion and velocity of a falling object. The physical principles we used were Newton's second law, the velocity update formula, and the position update formula. The observed data was analyzed with Tracker, the GlowScript, and we had a GlowScript simulation with gravity and a GlowScript simulation with gravity and drag. Both simulations over-predicted how far the object would travel in the given time. Newton's second law allows us to relate an object's change momentum to the net force acting on the object. We used Newton's second law because the object was undergoing forces. Finding the net force on the object, we could calculate the total change in velocity of the object. We use the velocity update formula to let us predict the final velocity based on its initial velocity and the net force acting on it. We could iteratively calculate the new velocity of the object in each new time interval in our simulations. The position update formula allows us to predict the final position of an object given its average velocity, interval length, and the final position. Since there was forces, the average velocity is assumed to be the final velocity. We use this equation because it allows us to calculate the new position of each object after each new time interval using the position of the previous frame and the calculated velocity. The system is the crumpled ball of paper. The surroundings are everything else. The earth, the floor, the room, the air, you name it. The initial conditions are that the ball starts falling at the origin. The initial velocity is 0. The ball mass is 4.5 grams, and the frame rate of the video recorded was 38 frames per second. This is relevant for the delta t in the code. In this experiment, a crumpled ball of paper was dropped with a meter stick in the background. We recorded the object's motion as it fell to the ground. Then the video was analyzed with Tracker to obtain the position versus time data. In our two simulations, the top picture is in each column is the initial conditions, and the second picture is the loop. So for the initial conditions, the only thing that was changed was b, the drag coefficient, and for the loop, we can see that the net force in gravity only is just a factor of the weight, whereas with gravity and drag, it is the weight plus the drag force. And we set this up using a delta t of 0.03 or 1/30th of a second to match our 30 frames per second in the video. And we also used the velocity and position update formulas in each code to calculate the iterations, as you can see. So here's our data. The results are quite similar. Both simulations did underpredict the observed motion in the beginning and overpredicted the motion in the end. This could be due to human error in placing the tracker point at a slightly different location on the paper for each frame. It was slightly blurry at many frames. It could also be due to the angle at which the video was recorded, where it wasn't exactly aligned with the meter stick and the ball in the middle of the falling motion. The drag coefficients might also not have matched the experimental conditions that the ball was under at that exact time. So which model predicts our terminal velocity? The model with drag and gravity factored into net force would eventually predict a terminal velocity given a long enough time interval, although we did not encounter that in this time interval of the experiment. When the ball reaches terminal velocity, the gravitational force would be equal and opposite to the drag force. In other words, the net force would be 0. If the object was initially thrown downward, the terminal velocity would be the same since it doesn't factor in initial velocity. In GlowScript, regardless of the initial velocity, the terminal velocity was the same for each case. What changes is how long it takes to get there. Thank you for watching. Have a wonderful day.